Welcome to lecture 2 of the NITheCS SATACS course in category theory. We left off last time defining a category. So let's do a little bit of a recap exactly where we left off. We spoke of what a graph is. Just to remind ourselves, we can visualize a graph as a collection of dots which represent objects. And then between these dots, there are arrows that represent morphisms between objects. And there could be arrows in various directions, and there could also be several arrows connecting the same pair of objects. So this group of objects and morphisms is what we call a graph. And then we considered this idea that intuitively the morphisms represent processes between various entities. And we considered this idea that if I have a series of processes that takes me from a certain entity to another one, like this one, for instance, where we have what we call the path of three morphisms connecting initial object A with final object B, let's say. And we could have also another path, and then we discussed the idea of two paths being equivalent by the effect they have, by the final effect that they have. So somehow in a particular scenario where we have built this graph, we are able to detect whether the two processes, the two paths of processes have the same final overall effect. When they do, we say that they are equivalent to each other. And we could write this by putting this wiggly equality symbol there. If I want to formally write this out, the path of morphisms would be given by a sequence of index letters, let's say F and G. And we could say that, we could write that the sequence F1, F2, F3 is equivalent to G1, G2, G3, G4, the way I just did it on the screen. So this is a graph with equivalence. And of course, not everything needs to be equivalent to various things. So we could have objects that have arrows between that have not necessarily equivalent to anything. And this overall structure of the graph, together with the information of what is equivalent with what, is another layer over a graph, of course, the layer of equivalence. So we can temporarily refer this to as a graph with equivalence. And after that, we want to put conditions that the equivalence should satisfy. There are certain axioms that we identified. Let me remind you what these are. So we had the reflexivity axiom, the symmetry axiom, the transitivity axiom, the congruence axiom, and then a bit of a mess up at the end of the lecture. I wasn't sure myself what I was talking about, and so in the notes I refined what I wanted to say exactly. And so the additional two axioms we want to consider is that of the equality axiom and reduction. I hope that's how I'm calling them in the notes as well. For reduction, I'm sure, but I'm not sure about equality. but I think it's correct. So let's briefly draw pictures for each of these. So what is reflexivity? Reflexivity tells you that anything will be equivalent to itself. So if I've got a path of morphisms, it will always be equivalent to itself. And symmetry means that you can swap the order around. So let me call this path F, and let me call that path F as well. And so I'm going to use a single letter to indicate a whole sequence of morphisms to make it shorter. And so then symmetry can be expressed by saying that if F is equivalent to G, then G is equivalent to F. Transitivity can be expressed by saying that if F is equivalent to G and G is equivalent to H, then F must be equivalent to H. Congruence property says that if I have a longer path where some middle part of it is equivalent to something else, then I can replace the middle part and the longer parts will remain equivalent as well. So imagine I've got a situation where I have, let's say, F1 up to Fn, and then some other thing, let's say G1 up to Gm, and then H1 up to Hk. So that will be equivalent to a similar thing with the G's replaced with G primes. And there will also be potentially M prime there because the length of the G path can be different from the length of the G prime path. But this is now provided, so this is a consequence of the G and the G prime being equivalent. So if G is equivalent to G prime, then this can happen. But of course, we should make a remark here that this only makes sense, the right-hand side only makes sense when each of these are actually paths. So this bit should be able to stick to the G bit, otherwise it doesn't make sense to talk about the equivalence. The equality axiom says that if I have a path of length 1, so I'm just going to write it with round brackets and F in it to indicate that there's only one morphism in the path. Maybe I'll just call it F1. If that is equivalent to F2, then F1 and F2 must be equal to each other. And finally, the reduction says that no matter how long a path I have, for every path, and it could even be an empty path, which means that I just have one object and there is nothing happening to it. For every path of length n, so n could also be 0, connecting object A with B, there exists a single morphism let's call that morphism H, such that the G path is equivalent to H. So no matter how long path we have of processes, that's how we think of them, right? So if I have a sequence of processes, right, the overall effect that this sequence of processes has should be possible to describe using just a single process. And the example we had in mind here is that if let's say morphisms are train lines between cities, right, then I would want to have also morphisms that represent chains of train lines as a single morphism. So that's the idea there. Basically, a route. Now, what is interesting about this is that we can start with fewer axioms and then build some structure out of a graph with equivalence satisfying these fewer axioms that satisfies more axioms. Like, for example, there is a way to there is a way to begin just with this, for instance, and then introduce new morphisms into my graph, which will take care of the reduction axiom. We will come back to this idea a bit later. For now, let's just say that these axioms together, if we put all of them together, they define what is called a category. So a category is a graph with equivalence such that all of these axioms hold. So let's maybe we call them something. I think in the nodes they're called E1, E2, E3, E4. And let me quickly double check for the consistency's sake that the order in which I put E5 and 6 is the same, as it agrees with the order that we have them in on our nodes. Okay, let's see where we are. So yeah, I think it is the same. So this is E5 and this is E6. So a category is a graph with equivalence such that all of these axioms, E1 to 6, hold. Okay, so when we introduce a new concept in mathematics, it is very important that we have a very, very good intuition for it. How does one build an intuition for a concept? Well, first of all, it's very important that we understand precisely the definition. But maybe even before that, it is useful to link the concept with various concrete examples, which kind of reveal what the concept is for. So that's what we're going to do now. We're going to build some categories, and this way, hopefully refine our understanding of what a category is. And let us begin with something very simple. What would be the simplest beginning? If I want to build a graph with equivalence that satisfies these axioms and that maybe and surely has real life relevance, let's build something actually real, something that we experience in our real world, so that we can make this concept really well grounded. What would be the simplest beginning? What do you think would be the simplest beginning? Can you think of some entity and some processes relating these entities that would be the simplest way to start building a category? Any ideas? So what are we looking for? First we're looking for so to give an example of a category, right? So to give an example of a category, what do we need? We need to say what the objects in the category are. We need to say what the morphisms are. And we also need to specify equivalence to describe when is one path of morphisms equivalent to another path of morphisms, to specify equivalence. So any suggestions? What should we take as our objects, and let's make it as simple as possible. Makawi, do you want to make a suggestion there? No, I picked you because I saw that you were your microphone was unmuted. Sorry
So
about
I
that.
think like that the set category of sets is probably like the first example that comes to mind.
Category of sets is good. That's fantastic. I want something more concrete, something closer to our everyday life, something less mathematical for now.
So maybe roads connecting some destinations and cities.
That's a good one. We already had something like that before. Let's think of an entirely new example, something that we haven't seen in the previous lecture. And something that is not too many of those. So we want few objects so that we can actually describe the full information about the equivalence and the morphisms as well. Well, if none of you have a suggestion, then I have one. What about a clock? So what about this thing? And let's say we simplify a clock. We just have a clock that shows the hour. And let's simplify it even further. Let's say that it doesn't show in between the hours. So it goes from 12. Once the 1 hour has passed, it goes to 1. Then the other hour has passed, it goes to 2, and so on. So our object is going to be, so let's write this out. Example, clock. So our object is going to be the clock itself. But remember that we're not going to be interested in the clock through its internal structure. We're just going to represent as it is a single dot. Huh? Object is the clock itself. And because it's a clock, let's call it C. What about a morphism? A morphism needs to be a process that kind of describes the function of the clock. So because we only have one object, of course, all morphisms are going to be going out from that object and going into that object. So the domain and the codomain of all morphisms will be C. Can you think of oh, I see now that Yaya has suggested for us an even simpler example, an empty set. So a category where we have no objects, when we have no morphisms, and also then the equivalence is empty. That would work indeed, because if you look at the axioms for equivalence, none of them require that something must exist. So it is possible to consider empty graph with empty equivalence relation. Okay. Coming back to the clock, we want to model the function of clock, which is the fact that it shows the hours. So maybe we should pick as our morphism the process of the hand of the clock moving from 1 hour to the next one. So morphism is so there's only one morphism, and let's call this M. and it's is the movement of the clock. Change from 1 hour to next. And perhaps that's all we need. We don't want maybe any other morphisms. Let's just keep that as a single morphism. So we wanted a simple example. So we just have a single object, a single morphism. And now we want to describe equivalence. So remember what the idea of equivalence is. It should tell us when is a sequence of processes, when do they have the same effect as another sequence of processes. Any ideas here? How are we going to describe equivalence in this example?
So I think that this category is actually category of a group set 12. So I'll say modulo 12.
Yes, that's a good idea. Who is saying that? Is it you?
Alexander.
Yeah. So we are actually building up. It will not be a category, this one. You will see why. But we can create a category out of it, as I said before. We're building up something that will end up being Z modulo 12. You're quite right. So if you move the hand of the clock 12 times, it ends up being at the same position as it started. So perhaps our equivalence should say that the path that begins at C, obviously there is only one object, and that has 12 many M's in it. 1, 2, 3, 4, 5, 6, and so on. So there are 12 many M's. Let me put it here. 12 M's. That path is equivalent to what? So if I what do I want to make it equivalent to? If I got a position at hour number 1, right? So then 1 hour elapses, another hour. After 12 hours, it goes back to 1. So the effect of having 12 many M's in a path is the same as the effect of what?
Of having none?
Exactly. Yes. Thank you very much, Linda. Am I pronouncing your name correctly?
Yes, of course.
Thank you. It's the same as the effect of having none. Exactly. So that is equivalent to the empty path. The empty path from C to C. We can write the empty path as just round brackets with nothing inside it. Because if there were morphisms in the path, then we would write those morphisms separated by comma inside the round brackets, so that we can just write the empty path as just round brackets with nothing inside it. That could be our equivalence. Now it kind of makes sense, right? So because if 12 hours have elapsed, then the position of what we visually see on the clock will be the same as if no hour has elapsed, right? We wouldn't be able to tell just by looking at the clock that 12 hours actually have elapsed, right? But now let's check which of those axioms that we listed, which of these axioms are satisfied by this structure. So let's begin with reflexivity. Does reflexivity hold? So what is reflexivity? Imagine that I have a sequence of morphisms, a path of morphisms. In this case, it's only one morphism, right? So I have just a sequence of M's. And the effect of that should be the same as itself. That's kind of obvious, right? But there's a problem with what we said on the screen, because it seems like on the screen we just said that there will be only one equivalent pair, namely this specific one, being equivalent to the empty one. And if we want reflexivity, then we also need to have something like, for instance, this being equivalent to this, which we didn't point out before. So we have to maybe add that. Then we will start seeing that we have similar problems with the other axioms, so maybe we can be a bit more clever. And since this example does come from real life, we could maybe use our knowledge of it, and we could just say that we want, let me make it a bit smaller. So a path of M's is equivalent to another path of M's precisely when, maybe I'll even say if and only if the clock shows the same hour after it has moved. By moving, I mean the moving of the hand. It has moved. Okay, now I need to keep track of how many M's does each path contain. So a path of let's say K many M's is equivalent to another path of L many M's. If and only if the clock shows the same hour after it has passed, after it has moved K many times and L many times, starting from the same position, right? And as Alexander said earlier, in the end, this rule will essentially be telling us that when we divide K and L by 12, the remainders should be the same. Yeah. So K, so the first path is equivalent to the other one if and only if K and L are congruent to each other modulo 12. So this is a very simple rule now that describes for us the equivalence. Okay. We can now go back to looking at the axioms. Reflexivity. Well, in the case of reflexivity, K and L would be the same value. And of course, a number is congruent to itself modulo 12. So that's fine. Symmetry is also fine. If K is congruent to L modulo 12, then L will be, then the other way around as well. L will be congruent to K modulo 12, right? Transitivity is also fine. Is congruence fine? So what does that, what would congruence mean in this case? So imagine I'm going to draw, so let me first write down that we are checking axioms, checking E1 to E6 for this example. So we said that reflexivity is fine, symmetry is fine. By the way, if I'm saying something that you either don't agree or don't understand or don't follow, please do interrupt. Transitivity is fine. Now, what about congruence? So, so the picture for congruence is the following, right? So this is our unique object, and then there is some intermediate path here, and then it continues on. And here I have another intermediate path. And so because in this example, equivalence of paths is reduced by the length of the path, and in this specific picture, these lengths are as we see them. So we have three morphisms here. We have four here. We have 3 here, and we have 4 here. But of course, 3 and 4 are not equivalent, because 3 and 4 are not the same, are not congruent to each other, modulo 12. So maybe we want to keep the middle part a bit general. So let's say we had something here that was equivalent to 3. Let's say we had some number of morphisms. So anyways, let me just call this K, and let me just call this L. And what we know is that K is congruent to L modulo 12. And if the congruence axiom were true, this should imply that, what should this imply? So the fact that this path is equivalent to this path should imply that the longer one is equivalent to this longer one. That's what congruence is, right? So this should imply that 4 plus K plus, well, maybe let me write it this way. 3 plus K plus 4 is congruent to 3 plus L plus 4 modulo 12. Do we agree on that? Maybe if we're not very good at modular arithmetic, we might have to think about this a little bit. But if we go back to the clock, what we're saying here is that the clock is at a certain starting position, right? So the hand of the clock is somewhere. Then 3 hours have elapsed. Okay, fine. After that, certain K number of hours have elapsed, as well as L hours have elapsed on a different clock that was on the same position as the first one. But the effect of this K hours and the L hours is the same. So of course the clock had a uniform position here because just 3 hours have elapsed from certain starting position. And then after that, what the clock will show right here will be the same in both cases, right? Because the effect of K hours is the same as the effect of L hours. So the position of the clock will be uniform in both cases. And then some further 4 hours will elapse, and then definitely we will still find the clock showing the same hour, whether we were looking at the top path or the bottom one. I hope that makes sense. If it doesn't, please do ask. And if it does make sense, please confirm by writing in the chat so I know that my explanation is not too obscure. Fantastic. Thank you very much for the feedback. Okay, so congruence axiom seems to hold. What about the other two? The equality axiom and the reduction axiom. So let's first look at the equality axiom. What does the equality axiom say? Well, it says that if I have paths of length 1, and in this case, this will just be M and M, the morphism M and the morphism M. If they are equivalent, then they must be equal. Well, since in this graph, we only have one morphism, right? Of course, they will be equal because there's only one morphism. We can never take a morphism M and a morphism R because we only have one morphism. So 2 paths of length 1 will trivially be equivalent. the equivalence asks in the end these two morphisms to be equal, but we only have one morphism, so they will be equal no matter what the assumption was. So equality holds in a trivial way. And then what about reduction? What do you think of that? Do you think that reduction will hold? Okay, with Darius saying maybe not. Would somebody like to explain why not? What will make reduction fail?
Well, I think it holds.
You're not quite correct.
Hmm.
But just remember what our morphisms were. Maybe that will help.
Can you remind me the reduction axiom?
Yes, of course. The reduction axiom says that every path of length n that connects A with B, for every such path, there must exist a single morphism such that that path is equivalent to the path of consisting of just one morphism.
Okay.
So in our case, a path of length n will be a process of passing n hours, right? Because each morphism is passing 1 hour. So 1 hour after the other, n many times, will make n hours pass, right? Do we have a morphism that describes n hours have passed? We've got only one morphism, as Luke says there. We've got only one morphism. That's how we chose morphisms. We made a bad choice, but we have to live with that now. We've got only one morphism. And that describes passing of 1 hour. We don't have a morphism that describes passing of more than 1 hour. So if I take a path of already of length 2, then there is no morphism that there's no single morphism that will be equivalent to it, because there's only one single morphism that describes passing of 1 hour. And passing of 1 hour is not the same as passing of 2 hours. There is even shorter path that we're missing, that makes the reduction axiom fail. So I said that path of length 2 will not have a corresponding single morphism, because 2 hours is not the same as 1 hour. But obviously path of length 1 will have, because there is only one path of length 1 that's the passing of 1 hour, and it's equivalent to itself, so it's no problem. But yet there is a shorter path that has no equivalent companion. Who would like to point out which path that is? That's right, empty path. And remember, empty path corresponds to no time passing, or at least the clock does not changing its position. And we don't have a morphism describing that. We only have a morphism describing passing of 1 hour. So already the empty path fails the reduction axiom. And now you see we now have a scenario where we built a graph with equivalence that satisfies all the axioms except this last one. But we need the last axiom in order for this to form a category. And the way we can fix this situation is that basically the last axiom tells us that we should have sufficiently many morphisms. We should be able to describe the effect of any path of morphisms by a single one. So it kind of tells us that we should have a good supply of morphisms, right? And that's what we're missing here. We're missing, in this clock example, we're missing morphisms that describe passing of 2 hours. We're missing morphism that describes passing of no hours. We're missing a morphism that describes passing of 5 hours. If we're missing them, then why don't we add them? So why don't we change our graph? This would be changing the graph. We will be now considering a different graph, maybe something that deserves to be called a clock better than this one because it only had one morphism in it. So we could expand our graph, add more morphisms to it, the ones that describe any number of hours passing from 1 to 12. That's all we're interested in because otherwise the clock position becomes the same. And perhaps then we could get this thing to be a category. And it turns out that this will work. So we will be able to still have all the other axioms satisfied, but also the reduction axiom we will be able to make it satisfied. And what is interesting here is that we could do this not just with a clock, but with any graph with an equivalence satisfying these axioms. So if you've got any graph with an equivalence that satisfies all these axioms, you can always add to it extra morphisms that will make all the previous axioms together with the reduction axiom also hold. Those of you who are familiar with the concept of completion in topology, you can think of it like that. So take the real line. Take the real line, right? On the real line, you've got rational numbers that can converge to a real number. Let's say numbers that converge to pi. So if you only consider rational numbers, then this infinite sequence of rational numbers doesn't always converge to another rational number. So there's a kind of a hole on the real line, right? And then the whole idea of real numbers is that we want to fill in these holes. We could actually even define real numbers by convergence of rational numbers. So we could bring in those missing points to fill our real line. It's a very similar process, even though this is not about infinity here. We're just bringing in finitary things, but it's a similar process when we're lacking having representatives, single representatives for paths of morphism. We can bring them in, add them to our graph to fill this lack. Okay, any questions on this one?
I just wanted to ask, so these extra morphisms we're adding, we can even add a morphism which is 1.5 hours.
We could add that one, although we are not necessitated to add that one. Since our morphism was a whole hour, by counting finitely many whole hours, we will never get a fractional hour, right? Do you agree with that?
Yeah, that's true.
Yeah. So we don't have to add half hour and 1.5. We don't have to add them, but we could add them if we wanted to make our clock more complete.
Okay, I think thank you.
Can we change the objects on the clock and maybe also the morphism to make the clock complete? For example, like for objects, like we're using the hours from 0 to 11 or from 1 to 12, and then the morphisms now will be like which hour precedes which hour, and then
you want the objects to be the states of the clock itself.
Yeah, be the hours now. What if we do that? We do it that way. Will it make it complete?
That's a fantastic idea. Let's actually explore your idea. I really like it. So let's think of it as a different example because we're now really changing it a lot. So a different point of view on a clock. Let's think of this a clock version A and a clock version B. Due to Linda. Sorry. So what you're suggesting, if I understand correctly, is that we have 12 objects. We can call them 1, 2, 3, 4, Let me actually arrange them in a similar way as on the clock. So we've got 12 objects, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these are our objects. Maybe to emphasize that, I'm going to enclose them in a circle, okay? So these are our objects. And if I understood you correctly as well, we want to add a morphism for every adjacent pair of objects. So we'll have a morphism here, a morphism here. This is another way to write morphisms, of course, when you put the arrowhead in the middle. So we'll have all these morphisms. And now, what these objects represent, of course, is where the hand of the clock is showing, right? So the object 12 represents the state of the clock when the hand is showing on 12. And the object 1 represents the state of the clock when the hand is showing on 1. And the morphism here represents transition of one state into the next one. Okay, so I think this can work. What would the equivalence be? Well, if I have a path that now transitions from 12 to 1, right? A long path that begins at 12, does all the cycle, reaches 12 again, and goes to 1. Probably that path should be equivalent to the single one, right? And basically, we can say that two paths are equivalent when, again, the number of morphisms involved in them, these numbers are congruent modulo 12. And in that case, we are still not going to have completeness. We're still not going to have reduction, because we will need arrows for each of these. So we also want to add these arrows, right? So we want to add this one, we want to add this one, because now passing of 2 hours now is represented by half of these two morphisms, and we don't have a single morphism that represents that transition from hand being on 12 to hand being on 2. So we will have to add all of these. So I think in this case we'll have to do much more additions, and it will be a very, very, very complicated picture, but it will work. Are you satisfied with that, Linda?
Yes, I am.
Wonderful. Yeah, that's great. Yeah, it was a nice example. There is another suggestion in the chat. If we can complete the graph by adding more morphisms, wouldn't that make adding the notion of a basis morphisms useful, like sufficient morphisms with which we can generate the whole graph? Yeah, that's a good idea, Luca. So what we're really talking about here is the idea of basis. So, well, the concept of basis comes from vector space theory, of course, and when we define a basis, we usually already have a vector space, and inside that we define a basis. So in a similar way, if we have a category, we could define its basis to be some piece of it, so that every morphism in the category is equivalent to a path of morphisms inside the piece. Like, for example, in this case, right? The white arrows would have been the basis of the category we could create out of adding all the blue arrows. And in the previous case, once we would have extended this example, version A, with passing of any number of hours, then the single morphism we started off in the beginning would have been a basis for the rest. So it's a very good suggestion, Luca. That would be a useful concept to have, the concept of a basis. The reason why I didn't take that approach is because I wanted to consider situations where you still have your basis, but you don't have the things you create out of the basis inside your realm yet. Like in version A, originally we only had one morphism, so we didn't have the things we can create out of it as single morphism. But of course, also in vector space theory, you can start with a set, with a basis, and then build a vector space out of it. a generating set. Maybe it should be called a generating graph, Alexander. And the idea would be that it generates a category. In fact, we can even start with less. We don't have to necessarily start with all of these axioms. We could even start with a scenario where we don't even have equality. We don't even have congruence. We don't even have transitivity. We don't even have symmetry. We don't even have reflexivity. We can start with nothing and then build something that satisfies all these axioms. We kind of did that originally with the clock. Remember, in the beginning, we just wrote the single equivalence. And then we said, okay, this is not enough because we want all the other axioms too. So then we made it very, very sophisticated and very complicated and still it wasn't good enough because the reduction axiom didn't hold. But we can actually start with nothing. And let's maybe talk a little bit about this. How can we start with nothing and then actually build a category out? And that will be called by a name that was invented by French category. He was essentially founder of category theory in France, André Eresman. It's called a sketch. By the way, I didn't tell you much of history of category theory, but there is so much of it you can read online that I don't think it's necessary for us to talk about it here. I might tell you things that is harder to find online, like the name of this concept sketch that's was introduced by Eresman. The way we're going to define sketches here will be a bit kind of childish version of sketches that Eresman defines, just because his sketches are a bit more sophisticated, that are useful for more things than what we're going to do now. Okay, so a sketch of a category is a graph with an equivalence that does not need to satisfy any axioms. It does not need to satisfy E1 to E6. And this is really good news because, well, first I need to convince you that we can actually build categories out of it. But before I convince you of that, let me show you why this would be useful. So you can literally start with arbitrary set of objects and morphisms, right? And then literally propose arbitrary paths to be equivalent to arbitrary others, not have to worry about checking any axioms. And then with that starting point, you can build something that will satisfy all the axioms. This is really, I think, a fantastic luxury to have. That basically we can create categories out of everything, right? Out of anything. Let's see how this could work. Of course, the theorem that we can create a category out of every sketch is a long one. I don't think we will have time to explore all the aspects of this theorem. I will put this theorem in the notes, though, with, hopefully in a clear way, and one can understand it. But let's at least look at the essential parts of this idea, so that the rest will be just a matter of computation. So the theorem says, thank you, Fosco. It was a nice Wikipedia article that's been linked here in the chat. I can't find, I opened it now, but I can't find sketch in the sense of category theory, but perhaps you wanted to say something else there. Yeah, so yeah, you're right. So I think you were making an intuitive point that sketch draws a quick outline of the category, and indeed it does. Every sketch gives rise to a category. Now, this is a very imprecise statement of the theorem. A more precise statement of the theorem should describe to us exactly how to build a category out of a sketch. And the notes will contain more precise statement of the theorem. For now, let's just maybe even think of it as a conjecture and try to rediscover this construction ourselves. Okay, so we start with any graph, right? Objects, morphisms, and some relations between paths. And now we want to build a category out of it. So what should be the first step? Step 1. We want to expand our graph in such a way that the axioms are fulfilled, right? And we have 6 axioms, and we can try to attack each axiom one at a time. We could try to expand our graph so that axiom 1 is fulfilled, maybe. Then expand or maybe I should say sketches, expand our sketch more so that second axiom holds, then expand it further so the third axiom holds, and continues on. But once I reach axiom 6 and I've now expanded my graph significantly, now it has more objects and more morphisms and more equivalences. How do I know that in this expanded sketch, axiom 1 still holds? Let me visualize on the picture. So we start with a sketch. We expand it in such a way to ensure that axiom 1 holds, the E1 holds, right? We expand it further to ensure that E2 holds. But already here, how do we know that once we expand it further in this expanded sketch, E1 still holds? Because remember, we only ensure that E1 holds here. But now we did a different process, different construction. How do we know E1 will still hold here? And this is dangerous because if it doesn't, right, then we might have to expand the sketch further and further up to infinity. So it might be a very, very complicated construction. And in fact, yeah, so one has to be careful on which axiom one tries to fulfill first. Okay. This is one of the things that makes the theorem complicated. Any suggestions? What do you think should we fulfill first? Let's start somewhere and see what happens. Anyone? What? Yes, Motofela?
I think if we can start with ensuring reduction, and then we build in all these other axioms as we go, smaller, deeper inside to ensure that they are satisfied.
I really like your suggestion. I really like your suggestion. Let's do that. Step 1. We expand our sketch in such a way that ensures E6 holds in the expanded sketch. E6 asks for every path to be reduced. How do we expand the sketch so we achieve that? And let me draw an analogy here for you. One fine day, mathematicians have asked to have a solution for the equation x squared equals -1. No real number satisfies that, right? But now how do you produce a solution that doesn't exist there, right? Well, as you know, the solution is to invent a number precisely for the purpose of its square being -1. So this we want to do for every single path. For every single path, we want to invent a new morphism whose purpose will be that it's equivalent to that path. So in a way, because we're doing this for every path, we will basically want to think of that morphism as a kind of path that's now turned into morphism. So we don't really want to distinguish maybe too much between a path and that morphism, but we still should, because it should be a morphism. So we will employ the following symbolic trick for that. Add to the graph. So for this purpose, add to the graph formal, let's call them formal morphisms, like in a formal linear combination, like when we are building a vector space out of given bases, to the graph, formal morphisms. So formal morphism, and we will change now our round bracket, which was referring to a path of morphism, to maybe an angular bracket, which will now refer to a single morphism. And that will be from x to y. And this will be one of each for each path, f1 up to fn. So we want to do this for each path from x to y. And this is not enough. We don't want to just add the morphism, right? Just like with complex numbers, you don't want to just invent the number I. You want to force I squared to be equal to -1, right? So we don't want to just add the morphism. We want to force that morphism to be equivalent to the path. So we also want to add an equivalence. Add also the equivalence where the path f1, fn is equivalent to the single morphism f1 up to fn. So this seems to take care of, if I go back to that picture I had before. So this is my initial graph, right? Initial sketch, I should rather call it. Initial sketch. So I've got the objects and morphisms in there. Now I've expanded it in such a way that whatever path of morphisms I take here, let's say from x to y, it will find a companion, a single morphism that lies in the expanded graph, and that's equivalent to it. So it seems to take care of the reduction axiom as far as the paths chosen are from the initial sketch. Now, before I continue, let me look at the question that was just posted on the chat. Why can't we just add morphisms to have 2 times n squared in total to connect everything with everything. Wouldn't that make a category? Perhaps that would not be a particularly useful category, though. What properties of original sketch are we trying to preserve? Or is the goal to generate a category with least additional morphisms? Yeah, so that's thanks for that question, Luca. So the goal is indeed to generate a category with least additional morphisms. We want to, in as minimal way as possible, distort our original graph. What you suggested in the beginning, just to add morphisms between any two objects, I think that's what you suggested there, yeah. You kind of seem of suggesting that now any two paths from X to Y should now be equivalent to that new morphisms you will add. So this will make much more equivalences in our original sketch than we could have had. So we want to actually add as few equivalences as possible, so that the information about our original sketch isn't destroyed too much. Like if we go back to that example with the clock, right? If I had done what you suggested with the clock, then let's see what would have happened. So this example here. Remember, in this case, there was only one object. So if I've done what you suggested, it would have made 1 hour, passing of 1 hour be already equivalent to passing of 2 hours and equivalent to passing of 3 hours, if I'm reading correctly what you suggested. So it would have made too many things equivalent to each other. We don't want that. I hope that answers your question, Luca. So we've now added these new morphisms that are equivalent to the old paths, but after we added new morphisms, of course, we get new paths, right? So I could have now another path that was added. Let's say this one. And now suddenly I have a new path, the path of blue arrows. Will they also have a single morphism equivalent to that path of blue arrows? Because we want reduction to hold not just for the initial sketch, but for the whole thing, right? And I think the way we edit things, not yet. So just to show you an example here, if we, let's say, decide to turn, let's say we've got X, maybe I'll call this A, F1, well, let me call this A1, A2, F2, A3, F3, A4, and I want to continue that. I want to continue that list. So then I have, let's say, F4 going to A5 and F6 going to A6. So I would have added a single morphism here, which is now the path F1, F2, F3 turned into a morphism, right? I would have also added something here, which is the path F4, F5 turned into a morphism. But all of a sudden, now I have a new path, the path of blue arrows, and that also needs a companion, right? How do we solve this problem? Should we now keep adding more and more and more? What shall we do? So what do we do with the fact that we're now missing this arrow, the purple one? Any ideas on that? So this we've added, and we have equivalence. This we've added, we have equivalence, but now by reduction, with the path of blue arrows also needs to have a companion. And at the moment we don't have, it seems, or do it.
Well, the one generated by from F1 to F5.
That's an interesting idea. Let's see what happens there. So we do have something here that we've added, right? The longer path, F1, F2, F3, F4, F5. So maybe we should just require that this longer one must be equivalent to the path of the shorter path of blue arrows. So maybe we should just add this additional equivalence. But we have to be careful. We don't want to add equivalences just like that, for the reasons that we discussed earlier. We don't want to have too many things become equivalent to each other, then we will destroy our model. But it turns out that this equivalence, the blue one, would have been forced anyway, should all the axioms hold. And if it is forced anyway, should all the axioms hold, then it's fine for us to add that equivalence as well. But let me show you why that equivalence will be forced by the axioms. So why would that equivalence be forced? So I want to show you now, why would it be forced that this, if all the axioms hold, or if this was a category, why would it be so that this morphism must be equivalent to this path of morphisms? Okay. We already have that this is equivalent to that, right? That's the equivalence we enforced because we wanted reduction to hold. Now, by the congruence property, because this is equivalent to that, by the congruence property, this path will be equivalent to this path. Let's write this down. So by the congruence property, F1, F2, F3, F4, F5, that path would be equivalent to maybe I'm not able to fit it here, would be equivalent to the path with F1, F2, F3 here, and then F4, F5. So the congruence property tells us that if I have a long thing and some middle part of it is equivalent to something else, then I can just replace that and things will remain equivalent. So by the congruence property, we will have that. Then I can do the same replacement with this pair, right? Because of the equivalence I've got here. So this is further equivalent to, again, by the congruence property, if it holds, to this thing. Right? Where do we go from here? Any ideas? Transitivity, a good one. But let me leave that for as a last step. So, can I leave it as a last step? No, I can't. You're right. We have to use transitivity. So this first one itself is equivalent to this, right? And now I have a chain of equivalences. This is equivalent to that, just because that's how we introduced this morphism. It was something that would have been equivalent to that path. This is equivalent to that by congruence. This is equivalent to this by another congruence now applied on these two arguments. And in the end, we have a chain of equivalences by transitivity. Because this is equivalent to this and that is equivalent to this one will be equivalent to this one. But then, because this is equivalent to this and that is equivalent to this, finally, this one will be equivalent to the last one. So from these equivalences, we can, by transitivity, conclude that F1 up to F5, the morphism will be equivalent to the path F1, F2, F3, F4, F5. Is this clear for everybody? If not, I'm happy to re-explain some bits of it. I mean, that's what we wanted, right? We wanted to double check that this equivalence would be forced should we have been working in a category. We're not working in a category. We want to force this so we don't have to add too many extra morphisms. We want to kind of ensure that this extension we did, the initial extension we did, so this is our sketch. Let me call this sketch 0, because that was the sketch we start with. And then we did its extension to sketch 1. So this is sketch number 0. We want to make sure that the sketch 1 now satisfies the reduction axiom. And to make sure of that, it seems like we have to add a bit more equivalences to sketch 1 than we originally declared. What did we originally declare? We originally declared just these equivalences. The newly added morphisms being equivalent to the corresponding paths. But now we want also this, and we were a bit unsure, can we afford to have them, have these equivalences? And it turns out we can, because if I'm building a category, in the end, they will be equivalent to each other anyway by this proof. And so I can add this already at this stage. By adding equivalences like that, we will be ensuring that the new paths we get by extending my sketch number 0 with the blue arrows, the paths of blue arrows I'm going to add, they will still be reducible. Like in this example, as we saw, this path of blue arrows is reducible to a single blue arrow, which corresponds to the combined path of the reductions of the individual blue arrows. At this point, I really want to take questions to make sure that we all understand this well before I move on. Maybe you can just give me a reaction in the chat. Are you fine with where we are so far? Okay, great. How are we going to write? Well, at least one person said yes, and the others are showing the thumbs up, so I suppose that's fine. But how are we going to write this out? We still need to write it out. It was easy to write this one out, right? This one was easy to write out. How do we write out all these other equivalences we're going to add? Might need a bit of help from you there. So maybe we can say the following. I mean, that would be one strategy to try to write this out. But if it's too complicated, we might employ another strategy also, where we reach our final extension by intermediate extensions, which follows the requirements we needed for the axioms we needed for this proof. So what if we, instead of adding these equivalences, what if we rather don't do that yet? So so we did this extension from sketch 0 to sketch 1, right? Sketch 1 doesn't satisfy the reduction yet, but maybe we can extend it further by other axioms like congruence and transitivity, hoping that after these two more extensions, sketch number 3 will not only be satisfying equivalence and transitivity and congruence, but it will also satisfy the reduction axiom. So that could be a strategy. But as you start, I hope as you start seeing now, it's a complex theorem. So one has to carefully build the sequence of extensions to arrive where we want to arrive to. I think I'm not going to go further in this construction in this lecture because it will be a bit of too much of going down on a narrow path. My goal was to just give you a general idea what would be the approach. Let me leave you here with this topic. I will be writing notes, and you can also think about it if you like, and then you can also read on them in the notes, and then we could talk about this more in the next lecture. I want to talk about something else now. So, and so on. Okay. Now let's come back to our notion of a category and formulate another important, another useful fact about it. Another conjecture. What the second conjecture is going to do is to revise our set of axioms in such a way that it will be easier, in many cases, it will be easier to check that the thing we're working with is a category than doing this with all the 6 axioms that we have. And specifically, what I'm going to do is to revise the reduction axiom and also revise the congruence axiom. So, given a sketch, now remember a sketch is just a graph with equivalence with no axioms. So a sketch is a more general notion than a category. Every category is a particular case of a sketch. Given a sketch, let's call this something S. Satisfying axioms E. Let me see here. So I want to keep E1, E2, and E3, and E5. And I want to slightly simplify the formulation of E4 and E6. Actually, I want to simplify yeah. Okay, so given a sketch as satisfying E1, 2, 3, what did I say? It was the number 4 and 6 that I'm going to simplify. Yeah, so E1, 2, 3, and 5. Axioms E4 and 6 are equivalent to, so by this I mean the two together. Let me make it more clear. Axioms E4, 6 together are equivalent to E4 prime and E6 prime together, where E4 prime says that if I have a path of just four morphisms, okay? F1, F2, F3, and F4, where F2 and F3 is equivalent to a single morphism, let's say G. So we are given that F2 and F3, this path, is equivalent to a single morphism G, then the path of these four morphisms will be equivalent to F1, G, F4. And once again, it's understood here that F1 ends where F2 begins. So this actually is a path. I'm not forcing it to be. I'm assuming it is, and then the equivalence must hold. So basically, it's the congruence axiom, but I've replaced, I've simplified it, right? I don't need to have this to be of arbitrary length. I could just have it to be of length 4. And then the thing I'm replacing with an equivalent path doesn't have to be of arbitrary length either. It can just be of length 2. I also need, in the case of length 0, so the empty case. So if the empty path is equivalent to some G, then F2, F1, F4 must be equivalent to F1, G, F4. So I'm taking a special case of the congruence axiom where we are only focusing on a path of 2 or a path of no morphism being equivalent to another morphism. And I will do the same thing to reduction. So I'm only going to be forcing reduction when I have paths of length 2, but then I'm going to be adding something else instead. No, I don't think, sorry, I don't need to add anything else instead. It will be sufficient. So for any path, F1, F2 of length 2, there exists a morphism G such that that path of length 2 is equivalent to the path of single morphism G. Okay? And I want the same for the empty paths. So we have exactly one empty path for every object, because once I fix the object, there is only one empty path that connects this object with itself. So then I'm going to say for every object X, there exists a morphism that I'm going to call it E subscript X. Oh, maybe I'm just going to call it IX, but this is not the same I as the complex number I. There exists a morphism IX from X to X, such that the empty path is equivalent to the single morphism path consisting of just IX. So reduction is possible for pairs of morphisms in a path, and also the congruence is possible for that. With even further restriction that we don't need to care about having many surrounding morphisms, right? So it turns out that these kind of special case, I mean, you will agree with me surely that if I do have E4 and E6, then for E4 prime and E6 prime will also hold, because these are just special, very special cases of E4 and E6. But of course, the point of the conjecture is that these special cases turn out to imply the others if I have all the other axioms. And let's see why this is so. So I actually want to call this a theorem, because we're going to prove the theorem, although we will probably only give an outline of the proof. We will not worry too much about the formalization of the proof. Let's just try to prove with pictures. So we want to establish now E4 and E6. So first, let's remark that since E4 prime and 6 prime are special cases of E4 and 6, we obviously have that E4 and 6 imply E4 prime and E6 prime. So we're going to prove the converse. We now prove the converse. So we assume that E4 prime and E6 prime hold. And let's first establish the, which one shall we establish first? Let's establish first the congruence property. So the picture for the congruence property is that I have a certain path, right? Do I want to establish the congruence property first? Let me think about it. Maybe. I have a certain path, and I know that these paths are equivalent to each other, and I want to get that the longer paths are also equivalent. So I guess this is long enough. And by E4 prime and E6 prime, I can only make conclusions when things are of length 2 or empty, right? So what do we do here? Well, by the way, any ideas?
Maybe we use induction on length.
So we kind of want to slowly reduce things,
Yeah.
in that, right? So we could apply reduction axiom for, let's say, this pair to claim that this path is equivalent to a single morphism. We know such morphism exists, right? Then we can apply the reduction axiom again to claim that now this path is equivalent to this one, right? And I will add one more morphism here. So I have a bunch of blue morphisms that I've added to my picture. I can do exactly the same downstairs. So I can add a bunch of orange morphisms by combining the pairs. Maybe there is a more beautiful way of doing this. Let me do it in a slightly more beautiful way. Let me do this and that. And then for these pair of blue morphisms, we will have this. This is similar to the picture we had before, right? And then for orange ones, I can do this. Did I choose paths of the same length? That's unfortunate. I want to maybe change that, if you don't mind. Let's choose here something of length 3, so that we don't feel that some coincidences happen because of two things are of the same length. We do this, and here I can't be more beautiful, so I have to just do this. Now I'm going to claim that this final blue arrow let's label them first of all. So let's call this A, B, C. And let's call these D and E. We also need, I guess, names for the white ones. Maybe we don't need names for the white ones. So I'm claiming now that C is equivalent to E. I'm going to prove that first. Okay. Now, what do I know about A? I know about A that I've got this equivalence. Because A was produced by applying reduction for 2. In other words, by applying E6 prime. So I know that I've got that equivalence. For the same reason, I've got equivalence of this blue arrow with these 2 white arrows. Again, I'm applying reduction just for 2, and that's ensured by E6 prime. And then once I produce the 2 things, A and B, I again use reduction for 2 to get equivalence between C and AB, right? Okay, now I want to claim that, okay, well, first of all, I have something exactly the same on the orange side, right? I've got this and I've got this. And remember what I knew initially? I knew initially that this path of white arrows is equivalent to this path of white arrows. That's what I know in the beginning. And I want to conclude from this, that's what I'm trying to prove, right? That this longer path of white arrows is equivalent to this longer path of white arrows, right? So my initial step is that I've got this equivalence. I produce these ones by applying my assumptions. And now I want to claim that this blue arrow is equivalent to this orange one. Let's see if we can achieve that. So we will write this out the following way. So C is equivalent to the path AB by what we already have, right? But okay, this is where I do need those names. So let me call this A1, A2, and let me call this B1, B2. I'm going to call this D1, D2. I'm going to call this one just E1. So I suppose you will agree with me that I can use congruence for 2. In other words, I can use E4 prime to deduce that yeah, it's a bit complicated. Why? But we'll see now. To deduce that this is equivalent to the following. So I will just insert A1, A2 in the place of A. How do I get that? Well, I can't get it straight away because the congruence for 2 requires me to have something on the left as well as something on the right. Then I can replace these 2 with something it's equivalent to. In this scenario, I do have something on the right, but I don't have anything on the left. So I can't initially replace this with this pair. I need to have something on the left. But the second part of E4 prime allows me to replace empty spaces with something, you see? Maybe I led myself to a dead end here. I might be missing still some tools to proceed, right? Even if I add that empty place, the question is how can I add that? So what I want to do is now is to add this I morphism. So where is it? This one. I would want to add that here. I would want to replace this with I, and then what will be the subscript of that? Whatever the domain of A was. So let's call this domain of A. Let's say it is X. Okay. I want to say that AB is equivalent to that path with the empty thing inserted there. If I can say that, then I will be able to replace, I will be able to keep this ix here, and then do the replacement of A with A1, A2. So we still don't know this yet. Let's park that there for now. Let's see how we would proceed otherwise. So once I would have done that, I would have arrived here, and then I would do this. I would do something similar to the right side. Like I inserted I here, I would also insert some I on the other side to give me IX, A1, A2, B, and then if this is Y, then this would be IY. And then I would replace my B with I would replace my B with B1, B2, but there is another problem there, right? What is the other problem? Because I can only do replacement with 2 if I have a single thing on this side. And I don't, because now I have 3. So you see, this is not really getting us where we want to go. So it's becoming a bit more difficult than I guess we have time to solve this problem. So either I'm missing something in my formulation, in my assumptions. Either this is not quite correct, that these axioms need to be slightly adjusted, okay? Or we're not seeing the steps we need to take here. So one of the two. I think it's wise to leave this problem for next time because we only have 10 minutes left. But at least I hope this shows you the kind of the intricate process one can try to take in trying to prove this theorem. So it's not a theorem yet; it's still a conjecture, right? It's not a theorem yet. We have not been able to prove it yet, so it's still a conjecture. If any one of you will resolve this before I do, you can let me know in the WhatsApp, please, or you can email me as well. Okay. Now the point of this conjecture is that you see we've simplified the information, the axioms that the equivalences need to satisfy, and we can actually simplify things even more and more, and eventually by a couple of more simplifications, we can get the definition of a category the way it is usually stated in the literature. This process was kind of meant to be to bring us to the usual definition of a category. And we will definitely discuss that definition next time. Now, the advantage of the definition we started off, which is basically a sketch and putting some extra axioms on a sketch. The advantage of that is that it gives us a nice way of building categories. And of course, the process of building categories is through this conjecture that we were talking about, that we can begin with any data of morphisms and equivalences, and then slowly expand this, add more morphisms that are required by the reduction axiom, but also add more equivalences that are required by the other axioms to eventually get a category out of it. And an illustration of this we saw with our clock example, where we saw how we could turn a sketch which only had one object and one morphism that was describing passing of 1 hour, we could turn that into a sketch that now suddenly satisfied all these axioms. It still didn't satisfy the reduction axiom, but then we also saw that we could even take care of that by adding one morphism for every number of hours passed from 1 to 12. Any questions so far? Any bigger, maybe bigger picture questions or of what we did today and do you think that you're understanding the concept of a category better, or is it still a big mystery?
So what I'm interested now is to think how are we going to use this completion, because like it's kind of useful in algebra and topology, but I'm not sure if it sets useful in categories.
You're not sure of what? Sorry, Alexander?
Well, here we start from some sketch and complete it till its category, and I'm not sure if it's that useful or not.
What is useful? The construction, or
Yeah.
well, maybe that's a good question, because I could show you some insight into that. So there are many constructions already in algebra which are actually special cases of constructing a category out of a sketch. We saw here with the clock how we get integers modulo 12, right? But what about all natural numbers? So we can, I mean, intuitively, we can build natural numbers by taking number 1, and then we kind of add it to itself and add it to itself and so on. But we can really think of this as taking one object and one morphism, and then taking all possible paths with that. We will no longer be forcing these equivalences, which we did, because now we don't want 13 to be the same as 1. And if we don't force, if we take this out, then our clock example is going to turn into a system of natural numbers. It will not be just a set of natural numbers. It will be the monoid of natural numbers. The multiplication of numbers will correspond to adjoining to paths. So if number n represents path of length n and m represents a path of length m, when we put them next to each other, that's sorry, did I say multiplication? I meant addition. That's the same as adding the two numbers. So that's one insight. The other insight is that the monoid of natural numbers is actually a special case of a free monoid over an alphabet. And an alphabet is where you have a set of letters. So you think of them really as letters, and then you want to place your letters next to each other. Let's maybe look at that as an example. Language. We will now look at a language as a sketch. So we only have one object like before, and for every letter of the language, we have one morphism. So let's say we consider a simple language which only has 3 letters, A, B, and C. These paths, the paths of these morphisms can then be captured by writing these letters next to each other, right? So we get words. So paths of morphisms will be words with letters from the given alphabet. And so if we start with a sketch and we want to force it to become a category, so we want to force the reduction axiom, we will be building out of the sketch a category which will be essentially the same as what is called the free monoid over a set, or the monoid of words. where the binary operation is concatenation. The way this links to algebra more broadly is that you also have in other case of algebraic structures, you start with minimal information, and you want to build your algebraic structure with the minimal information. Like, for example, you want to take formal linear combinations to generate a vector space out of a basis. Or you want to take polynomial ring out of your coefficients and the variables. And so this construction of a category out of a sketch, from the algebraic point of view, is actually kind of a special case of a lot of similar constructions which build very important mathematical objects. Now, for our purposes, the reason for discussing this construction is not to say that the construction necessarily itself is useful. The concept of a category is useful, and why we will see that later on. But what is useful about this construction is that it guides you how to create examples of categories. It basically tells you that you can begin with nothing, and you can still build a category out of it. Does that answer your question, Alexander?
So do I understand that this construction is in some sense analog to free constructions in algebra?
Yes.
Oh,
Yes.
okay. Fine. That sounds better.
Yeah. It is indeed a very, very similar and special case of free construction.